us continue our discussion on the operational amplifier in the series of tutorials. So basically, in the previous tutorial, we have talked about the basic operational amplifier configuration and how they work. Now we will talk about further applications of operational amplifier. The first one is the unity follower circuit. Basically, this is also called a voltage follower circuit, where the output will be equal to input. So if you see the circuit here, let us assume if I provide a 1 volt here, okay, the output will be 1 volt. So now if the output and input are the same and the basic operational amplifier functionality is not seen, then what is the use of this circuit? So what is the use is basically, let us assume we have some microcontroller and we have to interface some sensor to this microcontroller. So the microcontroller pin will have some impedance requirements. So the sensor which we connect to the microcontroller should not load the microcontroller pin directly, so that you don't get a proper reading. Now in this scenario, there must be some interfacing circuit such that the microcontroller doesn't see the load directly, and there is some matching that is done with respect to this. So we will talk about impedance matching in future circuit. Now assume that you need some matching that is required between the input and the output. So to achieve this matching, you need an operational amplifier circuit. So this operational amplifier circuit, which in unity follower configuration, also called the voltage follower configuration, helps us to achieve that. So this configuration is also called a buffer circuit, where it helps us as a buffer between the interfacing circuitry and then the actual connectivity, like the microcontroller to which we need to connect. So this unity amplifier circuit you see here is achieved by just shorting the output to the inverting terminal. So now when you give 1 volt, you just get 1 volt because the gain here is unity. That is why it is called unity gain circuit or unity follower circuit. This is similar to the common emitter follower circuit, which we have seen in BJTs. So this circuit is exactly similar in functionality to that. Now if you go back and refer to your circuits, or the guys who are listening to this, if you go back to see some of the sensor interfacing circuits or digital interfacing circuits, you see a lot of these being used in the circuits. And there is one more circuit called summing amplifier circuit. So the need of this summing amplifier circuit is, let us assume I have a AC voltage, AC signal, to which I want to add some DC offset. So in these scenarios, you use this circuit. So now let us see what is the configuration of this. So which is provided to the input of the non-inverting terminal, and then through we have given them through the resistors. So the output is nothing but the multiplication of the gain of corresponding resistors into the input voltage plus the gain of this circuit into V/2. So that means the output voltage is nothing but the summation of the gain applied input voltages, you can see here. So the gain is decided similar to the inverting configuration, which is nothing but the ratio of the feedback resistor to the input resistor. So A1 is RF by R1, this is RF by R2. So this circuit is mostly used for mixing also, and adding some of the voltages in a simple applications. So we see a inverting configuration here. This can be used in a non-inverting amplifier as well. So you can add as many inputs as possible here, and you will get the summation of the circuits. The only thing is, as you add more circuits, that there will be some variation in the output that will be observed. So you need to decide upon how much to be added, such that the operational amplifier is not loaded. There is one more circuit called the integrator circuit. So integrator circuit, just to put what is an integrator. So basically, let us assume we have a waveform which is ranging from time t is equal to 0 to t is equal to some x. So now the area of this complete waveform can be calculated using the integration. So integration is nothing but adding the things over a period of interval. That's what we learned during our mathematics in the integral calculus. So that is what this does. So here, if you see the circuit, we had a feedback resistor and an input resistor for the inverting and non-inverting configuration. In integrator circuit, the feedback resistor is just replaced by capacitor, which meant the product of this RC determines the functionality of this particular integrator. So this integrator, if you see, can be used in ADC converters, wave shaping inputs, integration circuits. So when we say wave shaping inputs, you can see here a square wave when provided an input provided gives a triangular wave output. So this output voltage is calculated by using minus 1 by R1 into C1, the product of this, into integration of V input, which is nothing but here a square wave is given. So if you want to integrate over a period of time interval, you provide 0 to t, similar to the integration which we learnt in our college days. So integrator circuit basically used in applications where you just need to shape a particular waveform, or you need to calculate a particular area. So this is what an integrator does. There is one more called the differentiator circuit. The major difference between integrator and differentiator is that the positions of C and R are replaced, where R is in feedback and C is in series with the input. So this again, going back to our college days, a differentiator is nothing but it helps to know how much change has occurred. That means the rate of change of a particular scenario can be known. Example, for a signal can be known using a differentiation. Differentiation helps us to know that proportional change. So that is what the op-amp differentiator also does. So like, for example, if you see here, if you give a triangular wave input, here the slope is constant because this is linear. So that means the output is constant at here also. So here what we can say is the output voltage is proportional to the rate of change of the input. So example, if you give a triangular wave, it produces a square wave at the output. So as simple as that. That means this is helping us to shape the waveforms as per our requirement, and this also in the instrumentation where you want to measure the variance, this circuit can be used. Here the output voltage is provided by this, which is nothing but RC into dV by dt, which meant RC is the product of the resistor and the capacitor, whereas the dV by dt is the differential of the input, which meant it calculates the proportional change. So that the these circuits which we are discussing here can be used with different configurations in different circuits. Like here it's just a basic scenario. There can be some additional components that can be added. There can be summation that can be done similar to the summing amplifier with the same differential circuit. There should be some additional input and output circuits that are required in end applications to perform the actual functionality of the circuit. So these are all which we can learn based on the application based. Here we'll just get to know how these differential circuit and the integrator circuit are functioning. Please subscribe to our channel. Let us know if you want any information. Please comment in the comment section if you have any questions or clarifications or any corrections required for our video. Thanks for watching.